To our workshop in this last session of parallel sessions. We'll be talking about mathematical inquiry in the liberal arts. I'm Phil Hotchkiss, and this is Julian Flarin.
Good afternoon.
And so to get you started, I'm going to let Julian start, and he's going to set a bit of a context for you.
The first thing we'd like to do is just tell you about the audience, the Math for Liberal Arts audience. The 2007 CBMS report shows that Math for Liberal Arts is the fourth largest college cohort of mathematics classes. The fourth largest. That means it's an enormous audience. The CBMS also showed that it's generally taught as a lecture-style course. Their statistics were for two-year colleges, but at two-year colleges, 79% of Math for Liberal Arts are taught as a standard lecture-style course. Sandra Larson was just up, and their anecdotal data from their survey showed that the respondents to their most recent survey, only 3% of those courses taught using IBL were Math for Liberal Arts. When it's the fourth largest college audience and only 3% is IBL, we have a lot of possibility, potential there. So we would like to share with you what an IBL liberal arts course can look like. So to do that, we're going to tell you mainly what we do, because that's what we can tell you about. The work that we're reporting on today is part of a large National Science Foundation project. We have a TWOS grant for the next 3 years. We had a phase 1 TWOS grant. We've also gotten support from Mr. Harry Lucas. We'd like to thank everyone for that. So Westfield State University has about 5,000 undergraduate students, residential state college campus. We have two Math for Liberal Arts courses. The one that we'll be talking about today is Math 110, which is called Math Explorations. We offer 6 to 10 sections of that course every semester. There are 30 to 35 students per section. The typical student majors are art majors, history majors, English majors, philosophy majors, communication, criminal justices. The course helps satisfy part of the university's Common Core requirements, and it's frequently taught in classrooms with tables. Okay, so we have tables here today. What we don't have is wraparound blackboards, which is something that's very nice that we have. So what do we do in this course? We do mathematics. And so that's what we're going to model in here today, too. We're going to actually ask you to do some mathematics so you can really get a sense of what it can look like in a Math for Liberal Arts course. Okay? So the material that we're going to have you start with is from our patterns book. All of our 11 books, some more finished form than others, are outside on the main table where you registered if you'd like to look at them. They are all freely available as PDF files that can be downloaded from the web. Okay, so if there's anything you're interested in, if you'd like to use this for a course, feel free to do that. Now, we're not going to work through this entire chapter from this book. We're not? No, we're not. Oh. But this will be on the exam.
You guys all work together.
Here's what I would like you to do. I would like you to pretend that you've been working on this for a little while already, and that you know what Pics Theorem is. How many of you, in fact, know what Pics Theorem is? Okay, so that some subset of you knows what Pics Theorem is. For the remainder of you that don't know what Pics Theorem is, it is a result from combinatorial geometry or topology, depending on how you look at it, that allows you to figure out the area of any shape that's made on a geoboard, okay, which is just an integral lattice. There are pegs here. You put rubber bands around the pegs on this manipulative, and you make what's called the geoboard polygon. And the question is there a nice way to find the area of a geoboard polygon that only involves basic counting? Okay? Pics theorem says that there is. It's a beautiful, very simple result. It's also very useful. If you look on what is called page 33, you will see a picture of the last remaining glacier in Venezuela. And next to it, you'll see a picture of our colleague, Karsten Braun, who was walking around the edge of it with a GPS strapped to his shoulders to try to get some idea of the area of this glacier so we can see how it's receding over time. 2013 is the year of mathematics of planet Earth, seems appropriate. Okay, so here's the question. How in the world would you find the area of that shape? Oh, well look, it's almost set up as a geoboard when you have the coordinates on it. Pics Theorem is a perfect way to do that.
Sure, sorry.
Okay, so what I'd like you to do, you're the students for a little while today. Not for the entire time, but for a little while. What I'd like you to do is I'd like you to start on question 40, okay? And I'd like you to do questions 40 through 46. And then for now, you can cross off 47, 48, 49, and 50. But I would like you to start at 40. And after skipping through 46 through 47 through 50, we'll see if we can get through some of these, and you'll see what it's like to do these problems.
We strongly encourage you to talk to each other because that's what our students do. The next thing that I'm handing out here is some previous work that you would have done if you had been doing this course right along, and so it's got some information that you're being asked to go back and look at.
Okay, so if we could bring you guys back together again for a minute. How much time do you think just passed? Close to 30 minutes just passed. A typical thing in our Math for Liberal Arts class is that we have to do exactly what we're doing now. We have to call time out, and most days we have to tell students it's time to go. Class is over. When does that happen? I mean, really, they have no idea that class is over. They would work halfway through the next class, too, if somebody didn't have to come in. That's a good sign. Okay? So we turned this over to you. Are there questions, mathematical questions first, before we talk about kind of the IBL thing?
I couldn't work all the problems.
You couldn't? Okay.
In particular, the part where we find the interior measure, and it's the very first figure, upper left corner. This one, I don't know how to do that because I don't know how many degrees are in.
Oh,
And that was why we handed this out, because by the time they got to this point, they would actually have measured those angles using a protractor. Okay? And so that's why we handed this out. This was to help you do those questions. So yeah, I mean, that's part of what happens here is that they'll do some stuff and then we'll refer back to it later. So they're always kind of building on what they've already done. Other questions?
A comment about what's to come. If you look ahead a little bit more on page 35, down at the bottom, the kind of key idea, which I think most groups kind of started to intuit already, is that if you add up the visibility measures of those points, they equal the area, which at first is a very strange thing, that adding up angles gives you area somehow. Okay? But it's ingenious in terms of the proof, because if you take two non-overlapping geoboard polygons that share part of a boundary, the areas are additive. But guess what? The visibility angles are additive as well, where they share a boundary in the middle, in an interior, in a boundary point that's on the interior, not at a vertex. Each is a half plus a half as a whole. You have 360 degrees. At where vertices come together, you simply add those two together. So now you've transferred a problem that's about areas into something that's just about measuring angles. But they're both subadditive in the same way. So now you can start using geometry at the same time that you're just doing these sums. Okay? And in fact, this is kind of a baby version of measure theory that you're doing. Okay? But this is what proves Pics theorem. The main idea at the very end is that you just add up all the interior points. They're 1 at every single interior point. Every single boundary point is a half, except for the vertices. So what happens when you add up the interior angles of an n-gon? Well, you get some very predictable thing, which the students will also discover, and that's the last step, and that kicks out that -1, and you're done. Okay? So the context for this is that this is one chapter in one of these books. Typically, we use one book for a semester. Like I said, we have 11 books that are outside. You can look at them. They're available for download. It would take probably 6 or 7 50-minute classes to go through this material. Okay? That's about what happens. And what we've tried to do is model the way we would teach that class with you guys. So now we have a couple of questions about the use of inquiry here.
One thing I would also like to say is that the way we started this session in a lot of ways mirrors the way we start our course. We set a little bit of context for the course, maybe talk a little bit about the structure, hand out the syllabus, and then we hand them the problems and they start working. So again, we've done some modeling here.
And it models what we do every day, too. We
Yeah.
don't walk in and lecture. We might have 2 minutes worth of announcements or some other thing or clarifying questions, but we do mathematics. And in addition to the students not knowing when it's time to go, when the students walk into our classroom, they sit down, they get their stuff out, and they start working. You walk into our class 5, 6, 7 minutes before class is supposed to start. Whoever's in there, they're already working because they know what they have to do. They pick up right where they left off. They have the responsibility. They know where they are. So I think we'll put these up all at once. Does that make sense? Because they're related.
Make all of them? Yeah, sure.
Yeah. How is this approach that we just illustrated here similar to a typical Moore method approach? Actually, you're right. Pics theorem was told because we put it on the overhead, but that's only because you didn't do problem number 18 before you walked in here. So we, in fact, didn't even tell them Pics theorem.
Yeah.
But they're developing it all the way.
Yeah.
How else?
There's a list of questions.
There is a list of questions.
I noticed that.
Right. Before things start, there's not a list of definitions and theorems the way a typical Moore method, but there is a list of questions.
We all more or less worked alone and then talked afterwards a bit.
You all more or less worked alone. There was some discussion. You do?
Yeah. We tried problems, but we all got confused pretty quickly.
Uh-huh.
And so I honestly don't think we would have. I don't think we would have progressed without talking to each other. I mean, the questions would go back and forth. It's like, wait, how do you do 33 or 41? We didn't understand 41. We had to talk about it for a long time before we even could progress. So I didn't see it as working alone so much as really working together.
Okay.
Some of us had little bits of information the other people didn't have, and it helped us make progress.
Oh, I guess I'm answering the second bullet. How is it a little different from the Moore method approach? Is that okay for me to?
That's fine too.
This is a pretty sort of roadmap set of guidelines. You know, go this way. Now try doing this. Now and then try doing this. It's a carefully laid out path for that.
Yes.
Seems to me.
Yes.
I would like to add to that. That actually depends on who's using materials. Julie and I do this very laid out path. Our colleague, Chrissy von Renessa and Volker Ecke, they would probably only use some of these questions and let the students figure out the path. So you can do that much more open-ended and let them determine their path. Just the way we are, we're more comfortable with the...
So if your students are strong enough, once you kind of show them this picture of what happens with a rectangle laid justified, you can just turn them loose and let them go, if they have the mathematical maturity and the confidence in themselves to do that. But remember, we're talking about math for liberal arts. Okay, so that's often not the case with those students. So let me ask you a question, since the experiences in one group was that people were mainly working on their own and then they checked in, versus another group where there was more active communication. How would we as faculty deal with that in terms of assessment? Or how would assessment work at all? Can you envision an exam for this course, a typical exam? So what Phil and I both do is that we put the responsibility on the students. There's been a lot said about students' use of language. Okay, if you really understand how this works, whether you did it individually with very little communication or you did it with more active communication, guess what? At some point, you're likely to have a career where you're going to have to solve problems and explain to someone else how you solve those problems. Okay, well then that's your responsibility. Your responsibility is to submit something to us that shows that you've understood how to solve these problems and how to communicate that result to other people. And those solutions are individual things.
You're expecting students to give individual write-ups of what they've gotten out of it.
Yes, we do. Individual write-ups of what they got out of this, which is a grading nightmare of enormous proportions.
How is the grading?
Depending on how you do it, it's overwhelming. Because, you know, like one of the things that we do is, well, what Julian and I do, is if they're submitting solutions, you know, they'll submit all the solutions in chapter 3 or whatever this was. And then we'll spot grade 5 of them. I mean, you know, not spot grade, but cleanly grade 5. And we'll grade the same 5 for everybody. And my students quickly figure out that the ones that I'm going to pick are most likely the ones that are a synthesis one or something that involves with explaining the mathematics, you know, doing something, either a proof or mimicking a proof. So they know that they have to do all the other questions to get to that. We've also, Julian's done audio quizzes, you know, where they come into the office and do things like that, and also had them do videos. And we do open notebook quizzes where we just give them the question number and they write down the answer from the notebook. So again, they have to have their notebooks.
So a comment about this assessment aspect and then a question. I've actually done similar sorts of things myself in teaching a similar sort of course and feel it was wonderful, although it exhausted me. I typically, an activity like this will take, as you said, some number of days of class periods. So it's not as if I'm collecting something like this from a student every day. Instead, after 2 weeks of working on something like this, then they'll turn something in. Well, fine, I can read a paper from each of my students every 2 weeks on this, at least. And now, a question I would ask, and I don't know if you're ready for these kinds of questions yet, but so obviously this is highly dependent on every student being here in class to do the work. Otherwise, they're probably completely lost. So how do you handle students who miss days, aren't there? Oh, I'm sorry, my grandmother died last week. I wasn't around last week. I've come, you know, how do I make this up? But they've already missed it. I mean, it's already gone by. What do you do when students miss out on being there?
I have a very strict attendance policy, and so they can miss 3 classes a semester, and then that's it. And after that, their course grade goes down by 1/3 of a letter grade for every class they miss. So, well, like I said, this would take 6 or 7 classes, so that's over the span of 2+ weeks. So they're not going to miss that many classes. But in fact, if you're following something like this, the student knows exactly where they were. They know what classes they missed. When they walk into the next class, they see where their group is. They know exactly where that is. And in fact, a lot of times when students miss classes, they email me while they're gone. You know, and they say, hey, listen, I know I was going to be behind. I was trying to catch up. I didn't know what to do on problem number 27. Can you help me with that? That's a much easier situation to deal with than a standard lecture class where they miss the lecture and they don't know how to do any of the homework problems, and you have to kind of recreate everything at once.
And one of the things that we've both noticed is that attendance actually is pretty good because the students catch on that, I mean, if they're going to be successful in this class, they have to be there every day. And if they're successful, you know, they're in class and they're doing all the work there, yeah, they have homework, you know, they have to do a certain number of things, but it's not an overburdensome. And so they come to class anyways, even if it's an 8:15, which is our earliest class, you know, you'll have 30 students in your 8:15 class because they know they need to be there, and then they do it. So it doesn't turn out to be as quite a huge problem as you expect. There always are some students that just think they can blow it off, and, you know, You'd help them out sort of within reason and let them, let it fall where it falls for them.
But along those same lines, then, the student that misses, do you notice sometimes that, like, if there's a group of four and one of them was gone, that they'll start the next day and say, what happened, and want to be sort of refreshed? Does that typically happen? And if so, does it sort of drag down the other students who didn't miss?
The students who were there, if that happens repeatedly, they're not very happy that the other person's not keeping up, because they know what their workload is too.
Yeah.
It's also the case, if you look at some of this though, is that you can kind of skip ahead. So a student who's missed one class and who actually has been sick, right? They can kind of jump in where their group is and kind of fill in backwards, but still move ahead and have some context for where they are.
Do you give it to all, do you give them all the questions at once or in increments? Like, do you give them this whole packet?
I generally give them a chapter at a time, so I would give them a
But no one
packet
just goes
like
home
this.
and does it the whole weekend or anything like that? You don't have a problem with people going past it at home?
Some students do go a little bit farther ahead, but those are the students who, try to work to the best of their ability all the time, and I don't really see a problem with them working ahead.
Do you tell them what's going to be covered on a given day? Like, today we're going to cover 35 to 47?
No, because in my experience, I never have any idea what we're going to cover.
Yeah.
You know what I mean? The things that seem the hardest to me are the things that, and that's what's so great about inquiry-based learning, is that the things that seem like they're going to be the hardest for me usually turn out to be easier for the students. Things that I think that we're going to fly through just get jackhammered right from the beginning and are much harder, often because of my misconceptions about where the students are at. But that's why inquiry is so important.
So something weird, but like it seems like good students can become a problem, right? So well, I guess it could, especially when they get close to the end of the packet, right? Well, I guess you could technically say, well, here you go, here's the next one if you're kind of done. But do you never have? So do you ever have the situation where some of them worked on it at home more than others, and then since they tend to work by group? I mean, so they show up and say, well, I did it all. Here is how I did it.
I don't generally have that problem. I mean, part of it is because we don't work through this chapter, so you wait until every single student in the class is done. Because certainly some students are working through the material faster than other students, and you can't kind of use the lowest common denominator to wait till everybody's done, right? So when you get the sense that there is a significant proportion, what I do, when there's a significant proportion of the students who are nearing completion, I make the class aware, hey, listen, these guys are almost done. Whatever assessment we're doing, it's coming up soon, get on board. And so what that does is the students who are farther behind, they know they have extra kind of work to do at home to catch up and stuff like that.
And I've noticed that there always are, one or two students, the first time you give a packet out, they think, oh, I've got to do this for homework. I've got to do all tonight. So somebody will come in with like 90% of it done. But then as we talk about it, they realize that they don't. And I usually tell them, okay, here's where I want you to be by the next class. So they get a sense that they don't need to be all the way done. And that keeps the better students, because the good students get most of it at home. They only have to do one or two questions at home, and then they can do their other homework. And then the students that need more time, they will spend the more time on it. And so it keeps everybody at about the same pace. But yeah, the good students, you either have to kind of do something that sort of naturally reins them in, or just have a lot of extra stuff available. I mean, we have some further investigations in some of these, and you can just turn them loose on those. Or if somebody asks a really good question that's not part of there, and you don't want to spend a lot of time, turn it over to the students that are ahead. It's like, wow, that's really cool. Here, why don't you work on this? So.
I don't know if I'm leaping ahead in your scheme here, but I'm again comparing with what I've done. I'm very interested in the dynamic in the classroom and the way you play into it personally. To what extent do you spend your time watching everybody and only doing something if somebody comes to you and says, help? Or to what extent do you go around and check in with every student and every group and discuss things with them? How much help you give them when they're stuck? All this sort of thing.
what we tried to model today is exactly what we do. We wander around the classroom. Okay, so for every 50-minute class, 45 minutes the students are working and we're wandering around the classroom. How much help we give them depends on a lot of factors, where they are. The students, especially in the beginning of the course, are always fishing for answers. They're fishing for compliments. They're insecure about their work. And you kind of hijack their ability to be responsible and try to do their own thing if you interrupt that too much. So that's a very delicate balance. Our two other colleagues, Chrissy von Renesse and Volker Ecke, are actually in the middle of writing a paper, and they're going to give a presentation at next week's prep workshop that Stan is organizing, that is all about how to listen to students in an IBL setting and how to have responses that value their work and help encourage their work instead of kind of stopping them or cutting them off or something else like that. So hop on a plane and fly to San Luis Obispo, and you hop on a plane and fly to San Luis Obispo, and you'll get a real answer to that question, because it's an important question. It's a critical skill to learn if you're going to do IBL.
I think I know the answer to this, but I'm just going to ask it anyway. So do the students present? Do they get up and say, look, this is how I solved it?
No. Okay. Because that audience is terrified to be in this class in the first place. And so, but they do a lot of board work in small groups. So they get more comfortable speaking with each other.
Let me qualify that. That's not necessarily true. I think in Chrissy's classes, they have whole class discussions where people do share their solutions, and students will come up and put stuff on the board, and they will discuss it. So there may be some sharing. And I'm toying with the next time I teach is trying to do some of that and having students put stuff on the board and share, so that we can kind of agree on good answers and things like that. So you can do that, but the way we initially started it, no, there wasn't a lot of sharing.
And there have been good talks about things like that that I've heard here that have kind of challenged me, because that's also one way to get around some of the grading issue too.
Yeah, absolutely.
Sharing will happen when certain people get incredibly excited, and then they're able, then of course I might encourage them to share. And so yes, it's very, I guess what I'm saying is, I'm asking these questions, but I've got my own flow with this, and it's all these things work in just the right balance that you create.
Yeah.
Thanks.
One more.
Oh, sorry, Paul.
I was curious on kind of two sides of it. One, do you do any work that prepares them at all for the problem solving? Do you give them any sort of problem solving methodologies, even basic, ideas like the Polya ideas, and then on the other side, how do you start discussing what looks like a good answer? What's a reasonable place for them to stop? Because that's, to me, the Texas method, that was the presentation, was that allowed for that ability to qualify what's a good answer. And curious about that as well.
So I don't think any of us talk generally about problem solving, because we've seen that the students actively working on problems puts most of them at such ease based on where they were when they first came into the course, which is terrified, not wanting to be there, that it's best just to get them working on problems, and then it starts to seem perfectly natural. And we might talk about some of those things, and there's, you need to talk about what constitutes a proof and different proof types and things like that. That's part of the course, but not from the outset. In terms of giving them feedback, I mentioned earlier that we have wraparound blackboards. So for the early part of the semester, we have students get up and in groups write up their answers to specific problems, and then we talk about them as a whole. So it's not one person presenting isolated with everybody watching them, but everybody getting up in groups and then collectively sitting back down and looking around and going, okay, well there's a problem with that because and that's not phrased very well, and here's how we can fix that. And so we try to model that as we go early on in the course before we start hammering them with a red pen. Or
green pen in my case.
I'm springing off this last question because it seems like it would be a marvelous opportunity to have the students generate, can we generalize? Can we list a set of problem-solving strategies that we've used and make that our little checklist, what things we could do when we get stuck. After they've worked through a couple of these chapters, could they generate, and that would be a way of being metacognitive about the strategy of solving problems more generally. It'd be fun to try.
That's a very interesting.
That's a great idea, since that's one of the things we want them to get out of the course.
Go ahead. Being aware of time, I think we're going to move on to the next thing.
Students generating their own problem solving and communication strategies after wrestling with doing it themselves. So it does work.
Yep. Cool. Thanks. All right. Okay, so what we would like to do is we would like to share with you why we do this. Okay, we've been doing this for a bunch of years. Like I said, we're on our second NSF grant. Can this really change students' attitudes about mathematics, especially this critical audience? Okay, these are students, it's their last math class. Okay, they do not have a good attitude. They're going out to be citizens. Okay, we got a problem. So to give you a sense of that and how these materials work, this is some survey data. So this survey data was taken over 14 years or something. We have a new survey that we're developing, and we'll have finer data.
I mean, over half of them say that yes, they can describe something beautiful by the end of the course, that they think is beautiful in mathematics. You know, whereas more than half said absolutely not. You know, before almost 2/3 said they couldn't. You know, beforehand. And this one I really like. It's just about remember this class.
Which too has some issues. They could remember the class because the people
because
who
of the
taught
crazy
it
professor
were crazy, and you know,
Yeah.
I mean, there's lots of confounding issues with this. I think that Phil and I have conservatively taught over 4,000 students using this method, and I can tell you that the answer is that the majority of them are.
Yeah. Yeah. I mean, one of the things is that I find amazing is how many of my students, you know, will talk, you know, they'll tell me this was a great class, best math class I've ever had, and, you know, I've learned a lot. And we have some student comments.
Yeah, do you want to put them up?
Yeah.
We also have a couple videos that we're going to show. So this is from an English major who will calm down on her rant, but first a small quote from Albert Einstein. I want to know God's thoughts, the rest are details. As a writer, I can show you my thoughts and nothing more. I am content with that for my lot. It's preferable to the head scratching allowed by psychology. But mathematicians can show the world God's thoughts. And through actually studying mathematics for a semester, I got to see them too. That's pretty cool. This course changed how I speak up and speak out about what I'm being taught. I've realized this really is my education, and I shouldn't settle for being force-fed information and taking shortcuts. Although the shortcuts are easier and everyone loves the easier route, it takes deep thought and actually learning to finally grasp something you never knew and you feel proud of yourself for it. Wow, how'd you sneak that in so fast? I felt proud of myself so many times in this class when I finally had a problem click in my head that we had been working on for days and realizing how simple it was, but it was exactly the process that I needed to understand it. No matter how lazy I was feeling and how I wished I could just take the shortcut and get the answer, I now know that isn't learning. That is just getting by. I don't just want to get by in my classes. I want to learn and grow as a person. So the only option from now on is putting in the effort for the hard road to the answers. You want to show a video?
Sure.
We have some video clips too. All these quotes, all the video clips, all the data are up.
I know I love math, like it's one of my favorite subjects, and I always thought that it was so concrete and that there was one specific answer that you were getting to, and everyone was using the same equations to try to get to that answer, and you know, you'd get points off here for doing something wrong and everything like that. But coming into this class changed like my whole view of math. I know that there's some math, like now there's no definite answer. You don't necessarily, not everyone's necessarily going to get to the same answer. Like with the Maypole, like some of us would come out with, you know, one lineup of ribbon colors and someone would come out with a different lineup of ribbon colors. but somehow it would, look the same. It's just, it's changed my view, definitely. I don't think math is so concrete anymore. I don't think it's so like, this is what you have to do, this is how you have to solve it. I think it's more creativity.
And the Maypole is an activity that we do in our math and dance class, where they actually make the Maypoles and then analyze mathematically the patterns that they get.
We have to be like really confident in our answers in this class because our professors isn't gonna go
Just
by
give
and be like,
us-
oh yeah, that's right,
Yeah.
kind of thing. We have to be sure we understand it fully enough to be confident to say, yes, this is the right answer.
So that's what happened the first day, actually. We were trying to figure out the Sudoku and the Latin squares.
Yeah.
And he asked us, how many different combinations? And all of us raised our hands and we were like, oh, it's a factorial. We've got this. And he was like, how do you know that for sure? And we were like,
It's our teacher
oh,
told us.
that's what our teacher told us. And he was like, yeah, but what does that mean? And we're like, I don't know. It's the answer though, for sure. It's the answer. And from then, I've kind of questioned whatever I do now with this math class. So it's certainly opened up a new door. But I do wish that there was a happy medium between this kind of math world and the math world I had in high school.
I love that thing about, yeah, it's the answer, One thing I would like to add, when I was listening to the other comment about the right or wrong and you get points off here and you get points off there. One of the profound things that it's done for me, and I'm sure that I'm saying something that you all have recognized. When I started grading, my point of view was looking for where they screwed up and reward and sort of saying, okay, you screwed up here, you lose, you lose, you lose. Now I grade in what you did well. What's good about what you've done? And it's made a profound change on how I look at their work, because it makes me much more appreciative of the thinking that they're actually doing and more likely to be rewarding's not quite the right word, but I can't think of the word I'm looking for, but more rewarding and supportive of that and sort of understanding where they're coming from. And so it's profoundly changed the way that I grade.
It's about 10 after 5. What I think that we ought to do, since it's getting late and it's Friday, is we would like to take 5 minutes to tell you a little bit more about the project itself and about the materials that we have. And then for people who want to go, you can go, and anyone who would like to stay is more than willing to stay. We have a whole nother topic that we can work on if you would like to work on tangles. So as I said, this work was begun with support by Mr. Lucas, and then a small National Science Foundation grant. We have a larger grant now, a TWOS Type 2 grant. And the goal is to develop inquiry-based learning materials, very much like what you saw here, that will support a Math for Liberal Arts course. But we're aware that people would like to teach different things, that there's lots of different topics. If you pick up a typical textbook published for Math for Liberal Arts, there's 13, 14 chapters, and you know that you will never use all those chapters, but people like some diversity, and we have many interests in the group. So what we're doing is we are trying to write 11 books, okay? And a book looks like this, okay? It is about 100, 110 pages. It's about the right amount for a semester-long 3-credit course. Okay? Some of the books are slightly longer. That means that you could teach Math for Liberal Arts 11 semesters in a row and teach something different every semester. Okay? We have books in, the topics are dance, number theory, calculus, geometry, art and sculpture, truth and reasoning, patterns, games and puzzles, I don't know what else, the infinite, music, knot theory. These are all available as free PDFs that you can download. Okay? So how can you use this? Well, you can decide you're just going to jump right in and do it, which is often a good way to do it, and you can teach a whole course. You can say, you know what, I'm going to do knot theory. Boom, here's the book. Okay? We have money for beta testers and reviewers, okay, through the grant, so if you're interested in doing that, we're looking for people to volunteer. If that's a little bit too radical for you, that's fine. Take a chapter. Just do one chapter. Try this. I'm going to go back. I'm going to take my general education course of some flavor that I teach, and I'm going to try to do this just to see what it's like, and do a chapter, okay, and just see how that goes, and let us know. If you would like, you can move the chapters around in our books, okay? We have a topic index on our website, and the topic index has lots and lots and lots of topics. So they'll just zoom by exponents and scientific notation, okay? That's a little bit more typical than doing Maypole dancing in your courses. So if you're required to do exponents and scientific notation, and you want some inquiry-based stuff, you click on that, and here you go. It's in the Truth, Reasoning, and Certainty book under the existence of the square root of -1 and types of reasoning in those 2 chapters. In the book, Discovering the Art of Mathematics, the Infinite, it's in the chapter, The Very Large. So now you can say, okay, wow, there's some resources. So let me go look in this. It's a PDF, just download it. I'm gonna go look at that. Wow, that's not really gonna work for me, but maybe I'll go use this one, okay? So we have this growing topic index.
Could you do 4 chapters from the number theory, and then 2 from the knot theory, and then 1 from the...
There are certain dependencies in these books that have not been articulated very well right at the moment. But, you know, if you have some foresight about what you're going to do, it is certainly the case that you could
So you could sometimes and sometimes not, and you might want to read carefully before you just decide to do it.
And you can certainly ask us. You can email us and ask us, and we have a better sense of what the dependencies are. It's just the case that right now things are getting shuffled around a little bit more. And what we would really like to do is that these things are in very nice shape. They've all been typeset in LaTeX, and that's great. What would be nice is if the chapters could be kind of used more in a more modular way. So you could not only pick to do 4 chapters in one book, 2 in another, you could actually put them together in some way other than just using Adobe Acrobat to slam them together. So we're kind of in the midst of trying to figure out how to technically orchestrate that.
So for example, like in the Games and Puzzles book, those chapters are essentially independent. You could take any chapters you want. Whereas in, say, the Knot Theory book, you could still do it, but certainly stuff that you do in chapter 6 kind of goes back to stuff you've already done in chapter 2, so it's a little bit harder. And I think part of that's reflected that I wrote this on my first sabbatical 8 years ago, and we weren't thinking that the grant hadn't started yet. We weren't thinking about this modularity. Whereas by the time the Game and Puzzles book was written, we were already sort of thinking in that direction. So the more recent books tend to have a little more independence.
There's not anything with a statistics and probability focus, and there's not likely to be anything with this statistics and probability focus, because there are other people who are working on things like that.
Yeah, there are a lot of really good ones, and so we don't really want to duplicate. Yeah.
Okay. It's also true that the focus here is a little bit more on the arts and the humanities. It's not that there's no applications in here, but you know, COMAP and organizations like that have already written beautiful books. There ought to be still courses for the art majors and the history majors. So in the geometry book, there's lots of stuff about projective geometry and how you represent 3 dimensions and the interplay between 2 dimensions and 3 dimensions, because art majors, history majors, theater majors, English majors are interested in seeing mathematics from that perspective. As I said, we have a new website. Everything is available online, the books and everything. We also have a brochure about our project if you'd like to take one of them so you kind of have something written down. Feel free to contact us with any other information. And like I said, we have funds for beta testers and reviewers if people are interested. Awesome. Well, thank you so much for everything.